Welcome to my case study circle channel. In this video, we shall see how to perform the stress analysis of the trusses. In particular, we shall select a power transmission tower for doing the stress analysis using the ANSYS APDL software. Let us move on to the problem statement. So as discussed, we have got an electrical power transmission tower and we need to perform the stress analysis for the tower, which is shown in the figure, for the loads that is applied at the key point 5 and 8. So let us deeply observe the figure and then try to write the coordinates for the structure that is given to us. So before we start with that, let us understand the material properties and the geometrical properties. So the Young's modulus of the material of the truss is 200 GPa, while the area of cross section of each member of the truss is 5000 mm square, and the Poisson's ratio is zero point 0.3. So with this data, let us try to write the coordinates, which is very important for us to locate the key points in the active coordinate system in the software. So we'll assume that the key point 1 is at the origin. So you can just see that at the origin, the key points are 0, 0. And from the origin towards the right hand side, so the maximum width of the power transmission tower here is 12,000. So here it is 12,000 0 because the y coordinate is 0. Next, we'll consider the next step, that is 3 and 4, and the height is 6,000 from the baseline or the reference line. So the y coordinates are 6,000 for both 3 and 4. And here you can just see that it is very clearly given. The distance from the origin to this point is 2,400 and 2,400. So it is 2,400, 6,000. And here it is 12,000 minus of 2,400, which is 9,600, 6,000. Next, we'll go for the key points 5, 6, 7, and 8. So the total height of these key points from the base reference line is 6,000 plus 6,000, which is equal to 12,000. So the key point 5 is located at a distance of minus 3,000. Why? Because the total distance from 5 to 6 is 6,000. So in order to have this length as 6,000, so if you just take up 6,000 minus 3,000, then you'll be having this point as 3,000. So that is the reason why it is minus 3,000 here. So the height is 12,000. So minus 3,000 comma 12,000, and this is 3,000 comma 12,000. Next is 6,000 plus 3,000, which is equal to 9,000 here. So the coordinates are 9,000 comma 12,000 for the key point 7, followed by 9,000 plus 6,000 for the key point 8, which is 15,000 comma 12,000. Next is the key points 9 and 10, which is located at a height of 6,000 plus 6,000, that is 12,000 plus 4,500, that is 16,500. So the y coordinates are 16,500 and 16,500, and the points 9 are uh, at a distance of 3,000 in the x direction and 9,000 in the x direction for the key point 10. So these are the coordinates that we write, which is given here. And next, the loads are acting at the key point 5 and 8, and the magnitude of the loads are 1000 kilonewtons. So, with this understanding of the problem statement and detailing of the coordinates for the key points, let us move on for creating this particular structure in the ANSYS APDL software, apply the boundary conditions and also the loads acting at the respective key points, and perform the stress analysis. So, before we do that, let us understand the boundary conditions. At key point 1, the degrees of freedom are fully constrained, that is ux, uy, and uz is equal to 0. And coming to the key point 2, there is a roller support which tells that the degrees of freedom are constrained in the y and the z direction, but it is free to move along the x direction. So there is some displacement in the x direction, and the displacements in the y and the z directions are 0. So these are the constraints. So now let us see how to perform the stress analysis of this particular structure using the ANSYS APDL software. So these are the parameters that will be determining, that is the reaction forces, the nodal stresses, and the total deformation in the structure. So now it is time for us to create the FE model of this structure in the APDL and then perform the stress analysis. Now let us continue with performing the stress analysis of the truss structure using the ANSYS APDL. So now we'll begin with clearing and starting the new commands. So select do not read file, click OK, and execute the clean command. right click until replot, go for file again, select change title, and let us enter the title as stress analysis of Truss. So let us call it as the problem number 2. Click OK. Right click until replot. So you get the title here. So now it is time for us to select the discipline, which is structural. Click OK. Go for preprocessor, select element type, and let us add the element from the APDL library. Click add, select link, which is the element, and click OK. So link 180 is the element. Click close. Now let us define the material properties for the element chosen. So go for material props, select material models. So structural, linear, elastic, isotropic. So enter the Young's modulus here as 200 E3 or 2E5, and next the Poisson's ratio is zero point 0.3. Click OK and close this window. So now let us define the geometrical properties. So the selected member is link. So go for link, click add, enter the ID as 1 and click OK, and enter the cross-sectional area as given in the problem statement, which is equal to 5000 mm square. Click OK. So now let us go for modeling. Select create key points in the active coordinate system. So first we are creating the physical continuum, and then we are going to do the discretization. So here by default the first key point is 1, which is at the origin. So click apply. The next key point is the key point number 2, located at a distance of 12,000 and 0. That is the y coordinate and the x coordinate. Click apply. So next is the key point number 3, located at a distance of 2400 in the x direction and 6000 in the y direction. Click apply. So next is the key point number 4. So it is 9600 in the x direction and 6000 in the y direction. Click apply. So next key point number 5, which is at a distance of minus 3000 from the origin and at a height of 12,000. Click apply. So be careful whenever you're entering the number of zeros. So next is the key point number 6, and it is at a distance of plus 3000 and at a distance of 12,000 in the y direction. Click apply. Next is the key point number 7, which is at a distance of 9000, and then the height is 12,000. Click apply. Next is the key point number 8, which is at a distance of 15,000 and the height is 12,000. Click apply. Next is the key point number 9, which is at a distance of 3,000 again, and the distance is 16,500. So click apply. Next is the key point number 10, which is at a distance of 9,000 in the x direction and at a height of 16,500 in the y direction. Click OK. So you can just see that the key points are defined in the active coordinate system. So now it is time for us to connect the key points. So let us go for lines and select lines in the active coordinate system. So let us pick the key points and establish the connections. So 1 to 2, next is 2 to 3 or 2 to 4, next is 4 to 3, 1 to 3 again, and then we have got 4 to 7, 6 to 7, 6 to 3, 6 to 5, 5 to 9, 9 to 6, 9 to 10, 10 to 7, 10 and 8, 8 and 7. And next we need to establish the diagonal connections. So 4 to 6 is one connection, and next connection is between 6 to 10, and next is between 1 to 4. So this is the physical continuum that we have created using the key points. So after all the connections are done, so just click OK. So now the physical model is ready. So now we shall go for discretization, that is nothing but meshing. So after having completed modeling, go for meshing. select size controls, select manual size, and then select lines. Select all lines and enter the element divisions as 1 and click OK. So you can just see that this is the discretization that is being done. So now let us go for mesh and select lines and select pick all. So you can just see that the FE model is ready. So now let us go for plot and select key points, or before that go for plot controls, select numbering and select the key point numbers to be on and click OK. Now go for plot and select key points. Select key points. So you can just see the key points here, which is the number of the key points required for us to apply the loads and the boundary conditions. So now let us go for loads. Select define loads, apply structural displacement on key points. So select the key point 1, click OK, and select all degrees of freedom, enter it as 0, click OK. So you can just see that it is constraint here. Next, again displacement on key points, select the key point number 2, click OK, and now deselect all DOF, select UY and UZ, and the displacement value in both the directions are 0, so click OK. So you can just see that the roller support is applied. So now it is time for us to apply the loads in the command prompt using the template. So the template here is Fk, which indicates it is the force acting at the key point, and the key point number is 5, and the direction is y, and the magnitude is minus 1000 kilonewtons, so 1000 followed by 3 zeros. So click enter, so the load is applied. Similarly, Fk is the syntax. Next, the key point number is 8, followed by the direction, which is Fy, and then the lab value, which is 1000 kilonewtons. So you didn't give it as minus, so it is taking upwards like this. So in that case, what we can do is we have got something called as delete. So select structural, select force on key points, and select the key point number 8 and click OK. So it is asking the force or the moment to be deleted. Click Fy and click OK. So now you can just see that the force is deleted. So now we'll reapply the force. So Fk, the key point index is 8, the direction is Fy, the magnitude is minus 1000 kilonewtons. So it is applied now. So we have applied the boundary conditions and as well as the loads. So this is how you can apply and delete the loads, that is on the key points of the nodes. So now let us go for solution and select solve the current load step. Click OK. The solution is done. So now let us extract the results from general post processor. So go for the general post processor, select list results and select the reaction solutions, all items, click OK. So you can just get the values of the reaction solutions at the node 1 and 2. So just do not get confused between the nodes and the key points. So these are the node numbers. So the node numbers are 1 and 2. So this is the direction Fy and this is the magnitude of the reaction force. So you can just go for plot controls, select numbering, and then switch on the node numbers and click OK. Go for plot and select nodes. So you can just see how the node numbers and the key point numbers are different. So the reaction forces are at the supports. So this support and here. So that is how you get the reaction solutions. And then go for plot results, select the deformed shape, deform plus and deform, click OK. So you get the deformed shape and this is the displacement that you get to see. This is the deflection or the deformation that is happening with the structure. So the blue color line indicates the deformed structure and the white line indicates the undeformed structure. So now just enter SAT in the command prompt, and next let us go for element table and select define table, click add, select stress by sequence number, LS, that is the linear stress, enter 1, click OK. So you can just see that the label is appearing here. Click close. Now go for plot results. Select contour plot, element table, ls1, average. Click OK. So you get the distribution of the stress. So this is the magnitude of the minimum and the maximum stress, which is distributed within the member. So as per the color legend or the scale that is shown here, you can match it up. So next, let us go for list results. Select the element solution and select stress 1 mises. Click OK. So you get the nodal stress. So these are the values of the nodal stress. So go for plot controls, select animate and select the deformed shape, deform plus and deform, click OK. So you get to see the animation of the deformation. So the deformation is going to occur where the load is applied. So these are the node numbers, that is 7 and 10. So these are not the key points. Instead, it is the node numbers. So click stop and click close to end the animation. So go for plot controls, select multi-window layout, select two left and right. So we're going to divide the screen into left and right. So click OK. So you get the screen like this. So now go for plot controls, select multi-window layout. Okay, we already defined the layout. We'll go for controls now, multi-plot controls. Click window 1, click OK. With the entity plots on, go for deformed shape, click OK. Deform plus undeform, click OK. Right click until replot. So you get this. So in order to fit this structure to the screen, just use the option here. So we have got a fit view. So select this, you get the object fit to the screen, displaying the deflection in the window 1. Go for plot controls, select multi-plot controls. Now let us select with window 2 and entity plots, click OK. Go for element solution, click OK. Select stress, and then let us pick up the one miser stress, deform plus undeformed, click OK. Right click until replot. So you get the distribution of the stresses here. And if you don't want this, just go for plot controls, select multi-plot controls, window 2, click OK. Go for element table, click OK. Right click until replot. So you get the values of the stresses that is being displayed here. So go for plot controls, select view settings, select style, size and shape, and click on the display of the element on, click OK. So you get the 3D view of the member. Similarly here, go for plot controls, select window 2, click OK. So if you want to show any other results in the window 2, go for clicking the particular parameters. So you get the member which is deformed like this. So if you just want to change the view, just go for view and select isometric. So you get the isometric view of the truss member, which is facing the deformation and the stress distribution within the member that is being defined here. So these are the different views of the member, displaying the deflection and the line stress. So go for plot controls, select write meta file, invert white or black, and save this meta file as truss 2. Click save. So just go for the destination, select the folder in which it is being saved. So just open it, and then you can save it as a JPEG image. So this is how you get to see the results in the white background. So go for file, click save as a JPEG pic, and then you can just save this as a JPEG pic. So with this, we complete the video which details about the creation of the truss member as per the problem statement, application of the boundary conditions and the loads, and then studying its deformation by knowing its deflection, that is the deformation, and computing its stress values and the distribution of stress within the member due to the application of the loads, and also the reaction forces at the supports. Thank you all for watching.